Hi, welcome back. We're in lecture 23 and the topic is the generalized linear model. In the first segment, we just introduced the conceptual overview of a generalized linear model, and now I want to show you just a couple examples of different link functions that we can apply to test nonlinear regression models. So remember that GLM star, the generalized linear model, is just a simple extension of GLM that allows for non-normal distributions in the outcome variable and therefore allows us to test nonlinear regression models. It's appropriate when simple transformations or quick fixes or product terms in the GLM just won't satisfy our needs and satisfy sort of the complex data that we're dealing with. We have to move to this more generalized linear model. And the key to the GLM star, this generalized linear model framework, is the link function. And the link function can be anything really. I'll show you just a couple examples in this segment to show you how it works and show you the versatility of this mathematical model. So one that you've seen already is binary logistic regression. Remember that binary logistic regression doesn't satisfy the assumptions of GLM because the outcome variable is not continuous and normally distributed. It's just categorical and binary. It's 0 or 1. Like in the example where we were trying to predict how a juror would vote, whether they would vote for a life sentence or the death penalty, that was just a categorical outcome 0 or 1. So we had to apply binary logistic regression. We had to apply a link function, if you will, on the left-hand side of the regression equation. So remember, here's the logistic function or logistic curve. The key is that we could have any sort of set of values of x, and when we apply this logistic transformation, we're going to wind up with predicted scores on y that fall between 0 and 1. And that was necessary in order to satisfy the requirement that we get predicted scores that wind up landing near 1 or near 0. So in binary logistic regression, the logit function served as the link function. So we actually have already done an example of generalized linear model. And we did that, if you look back at the binary logistic regression lecture, remember that in the R output, we had to use the GLM function, not the LM function. So the GLM function stands for generalized linear model, not general linear model. And that was done just by applying the logit transformation over there on the left-hand side of the equation. In R, remember, the argument in the GLM function is called family, and we just put in family equals binomial. And by putting that in to that function, GLM in R just did this for us. So the GLM star, generalized linear model, and the GLM function in R are very powerful and can test all sorts of regression models. Not necessarily linear, could be any kind of function we want. If you have more than 2 categories, so we didn't go beyond binary, but you could, right? So if you had 3 categories or 4 or more in your outcome variable, then that's just multinomial logistic regression. Again, it's still just the logit function that we would use as the link function, but you would need to create one group as the referent category and then create several logistic functions to compare each to that reference category. In the same way that we created dummy codes for categorical predictors, right? Because this is a categorical variable. If we had a categorical predictor with multiple levels, then we had to create dummy codes. One level served as the reference, and then we created as many codes as we needed to fill in the rest of the categories. Same exact logic applies here. That would allow you to do multinomial logistic regression, and you would do it by using this mathematical framework GLM star and the function GLM in R. Just one other example I'll mention here. Again, there are several. You could do a whole course on this. So I'll just mention one other example because it's sort of popular, is a Poisson regression. So a Poisson regression is necessary when you have a Poisson distribution in your outcome variable. And Poisson distributions are common because they deal with what I call count data. So count data are things that that occur as like number of events occurring in a specified time interval. So the example I'll use here are like the number of traffic accidents that you might observe as a function of weather conditions. So we talked about traffic accidents as a function of talking on a cell phone, right? But regardless of that, you could just look at traffic accidents as a function of weather conditions. So this is like difficulty in the driving simulator. So under clear weather, under rain, under snow. And what you typically observe with Poisson distributions is you don't get normal distributions. You get these distributions that sort of look like these in this graph because we're dealing with count data. They're cumulative. So in this example, what we're looking at is number of traffic accidents as a function of weather conditions. So when it's clear, this is over time, when it's clear, there's not many, but when it's raining, there are more. And again, we're doing this over time. We're counting them. That's the Poisson distribution. And in the snow, there's even more. And over time, they accumulate even further. So these aren't forming linear relationships between x and y. They're forming what's called a Poisson distribution or Poisson relationship between x and y. So to do a Poisson regression, we just use this GLM star framework, the generalized linear model framework, and just apply a different link function. And in this case, it's the log function. So instead of doing logit like we did for binomial or multinomial regression, we'll just apply the log function as the link function. And that allows us to test a Poisson regression. Now note, I have a note right here. In this example, we were also looking at traffic accidents in different conditions, right? So in clear weather, rainy weather, snowy weather. So we would also have, that's a categorical predictor, so we would also have to dummy code and add in those dummy codes for this example. So that would be actually a really good one for nonlinear regression. But again, we're sort of getting beyond the scope of this course. That's why I'm introducing this at the end here, just to illustrate that there are lots of other possibilities beyond what we covered in this course. We emphasized normal distributions in the outcome measure and linear relationships between the predictors and the outcome. But that's not necessarily going to be the case in all the data that you encounter. So just be aware that if you can't satisfy those assumptions, there are alternatives available to you. And they fall under this framework of the generalized linear model. And all I did in this lecture was just present an overview of that so you're aware of that generalized linear model. And here I just wanted to show you a couple examples, the binomial logistic regression and the Poisson regression, just as two examples of this. Again, you may encounter different types of examples, but the GLM star mathematical framework will allow you to test for those more complex nonlinear regression models. So to wrap up this segment, just remember that the generalized linear model is an extension of the general linear model that allows for non-normal distributions in the outcome variable and therefore allows you to test nonlinear relationships between a set of predictors and that outcome variable. It's appropriate when simple transformations or the addition of simple product terms don't allow a quick fix and don't allow you to stick with the LM function in R or that linear model. And the key to the generalized linear model is it applies this link function to the left-hand side of the equation, to the left-hand side of the regression equation, and that link function varies depending on what kind of nonlinear relationship you want to test in your model.